Yeah.
The last talk will be by Dimitri Pimenov from the University of Minnesota. The title is Twists and Turns of Pairing from Repulsive Dynamical Interactions. The Zoom is yours.
Yes, thank you. Yeah, thank you. So this is a work I did with Andrei Chubakov. So let me jump right in and start with how does one have to understand pairing from a repulsive interactions in a standard kind of case. So first of all, if you have an interaction which is just a function of momentum, here is a function of the angle on the Fermi surface, then you can have you have to solve the gap equation in the mean field approximation. And if the interaction is purely repulsive, in here it's a constant, then you cannot solve the gap equation, or the only solution is delta equals to 0. Because basically the left and the right-hand sides of the equation have opposite signs. But we know that if the interaction changes on the Fermi surface, so it's kind of changing as shown here, then you can have a gap, you can solve the gap equation, but the gap function just needs to have nodes on the Fermi surface. And when you have these nodes, the constant repulsion, which is this dashed line, drops out of the gap equation. And of course, this only means that you have a pairing in a higher angular momentum channel, D wave, for instance, while the S wave channel is repulsive. So the question is now, can we have pairing if we have a repulsive interaction, but we have purely S wave interaction? Is this possible? And the answer is yes. That's possible if the interaction as a function of frequency transfer, so changes on the Matsubara axis. So we're going to look at the following toy model. So where we have interaction, which is this function of the frequency, it consists of two parts. First of all, there's a instantaneous Coulomb repulsion, just kind of a repulsive interaction between electrons coming from Coulomb. And then there's an attractive part corresponding to an interaction mediated by some retarded boson, for instance, a phonon or a plasmon. And then there's interaction, you have some UV cutoff, lambda, which is supposed to be of order of the Fermi energy. And this could be viewed as a toy model for interaction of electrons in a realistic material, more or less. So in the old days, this was studied in the BCS limit, where this UV cutoff, the Fermi energy, is much larger than the energy scale omega d associated with the boson. So kind of dBA energy, and this is the standard BCS limit. But in recent times, it has only received kind of new attention because it's of relevance for low density materials, where actually the Fermi energy is of the same order or even smaller than the dBA energy. This is, for instance, the case in strontium titanate. So I'm going to look at this interaction, and I'm going to just use this as a toy model and trying to solve the gap equation and see what behavior we can get. So the gap equation now lives on the frequency, kind of function of frequency and Matsubara axis. You also already saw kind of a more complicated version of this in Andrei's talk before. So okay, you have this gap equation, and the interaction now. Let's look at the interaction. So if this coefficient f here, if it's smaller than 1, then the interaction has an attractive part at small frequencies. But if f is larger than 1, then the interaction is purely repulsive. But still, although it's purely repulsive, we can again solve the gap equation, and we find a finite solution, which is typically such a symmetrical gap function on the Matsubara axis, and it has two nodes on the Matsubara axis. So these nodes, they are somewhat non-trivial characteristic, because they can be interpreted as a dynamical vortex. So just a quick recap. So far I've discussed the gap function on the Matsubara axis. Now you can do an analytical continuation to the upper half plane. Then you get the retarded gap function. And then, so this dashed line here in this picture is the Matsubara axis. And then if you have a node on the Matsubara axis, then the phase of the retarded gap function winds by 2 pi on a contour encircling this node. This just comes from properties of an analytic function. So node can be interpreted as a dynamical vortex in the problem. Now the question is, okay, what about antivortices? Are there antivortices? And the answer is no, there are no antivortices, because an antivortex would correspond to a pole of the retarded gap function. This is known as Cauchy's argument principle. But by construction, this retarded gap function in the upper half plane does not have any poles. So you have only this kind of vortex, you have no antivortex, and well, question is what happens to this vortex? How can this vortex appear or disappear? And if you want to maybe just quick, if you want to look for physical quantities, then okay, we have to go to the real axis. And then in principle, for instance, the vortex leads to winding of the phase of the retarded gap function on the real axis. Okay, so our question will be, so we have a vortex and we want to see what it does. So as a function of the repulsion. So first we have this interaction, and let's say we don't have any repulsion. So the F is negative. Then the gap function does not have any nodes. It's just as a single sign. And now if we make F equal to 0, then basically it's kind of a, if you wish, a topological phase transition, and the vortex appears at infinity. Yeah. So there's no vortex here, and the vortex will appear at large, infinite frequencies, and then it will move to smaller frequencies if the repulsion is increased. So for small f, the position of the vortex follows this kind of law. If f goes to 0, the vortex goes out to infinity. Okay, now we have f, we increase f further. At some f, if you have a finite UV cutoff, then generically the frequency variation of this interaction will not be sufficient to ensure superconductivity. So at some point you will just go into the normal state. So this is this kind of picture. If f is smaller than a critical f, then you have a finite solution for the gap equation. And then for larger than a critical f, you only find the kind of 0 solution. And the question is, what happens to the vortex in this kind of transition? And it's somewhat a small paradox, because you would consider that the vortex stays at a finite frequency, and then you look at, again, our gap equation. Then basically, at the smallest frequencies, if the gap function size, basically gap function at 0 frequency, if it vanishes, then on the right-hand side, you would get this kind of Cooper logarithm, 1 over frequency on the right-hand side. You integrate over, so you have a logarithm on the right-hand side, but you have no logarithm on the left-hand side. So that's kind of, you cannot solve the gap equation. On the other hand, if you would say that the vortex goes to 0, just kind of simple, then what you basically find is, again, this nodeless superconductor. So sign preserving, and then, okay, but you're purely repulsive. So how can you how can you find a solution? And the answer is, okay, just the gap size, basically delta of 0, and the vortex position, the node, they have to vanish in tune with each other. So you can, in this model, you can find with some kind of logarithmic approximation, you can find the critical f, which behaves like this. Then if you approach the critical f, the gap size basically will vanish exponentially fast, while the vortex position will only vanish as this kind of power law. So look at the left picture, you see that the gap kind of decreases sharply, while the vortex position only moves a little bit. And you can also check this numerically. Now, one other interesting thing in this context is the behavior of the phase fluctuations. So we already had the superfluid density as a player a couple of times in this session. So, okay, so I'm going to look at this. Okay, I can write down an action for the phase fluctuations, and the superfluid density appears as a coefficient. Yeah, QA is the total momentum of a Cooper pair. And now the superfluid density for in this configuration, where the gap function depends on the frequency, can be shown to follow this behavior. And now, if you modify this parameter f, then because the gap function will change, the superfluid density will change. But interestingly, if f becomes larger, so it approaches a critical f, then the superfluid density will be locked to this basically BCS kind of value. And this can be understood from the fact that this integral here will be dominated by frequencies which are smaller than this delta of 0. But in this kind of limit where we approach the critical f, this delta of 0 vanishes very fast, while the the scale on which the gap function itself changes, this kind of node, is much larger. So basically, for the purpose of this integral, we can just approximate delta by a constant, and then you get back the basically BCS behavior. So NS, particularly if approach this critical f, it does not vanish, it just approaches this kind of constant. But what about basically continuity? Because in the normal state, it has to go to 0. And you can understand this as follows. So this kind of NS here is defined at 0 total momentum. But if you define NS, which depends on the total momentum, then at any finite momentum, it will actually vanish because it follows as a function of this kind of scaling function. And if delta goes to 0, then at any finite momentum, your superfluid density will vanish. From a physical perspective, you can say that basically the global phase stiffness is guaranteed, but then on larger and larger length scales, you will have wild kind of phase fluctuations as you approach this critical transition. With this, let me summarize. So we saw that with a dynamical repulsive interaction, and it leads to a gap function which has nodes on the Matsubara axis. These nodes can be interpreted as dynamical vortices, and the quantum phase transitions in the problem can be interpreted as kind of in terms of this vortex motion. One thing one could try to do is really extract some more physical properties from this vortex quantum number, maybe some kind of bulk boundary correspondence similar to topological insulators. And one thing I also want to flash, just an outlook, so something we are writing right now is that I only talked about these even frequency solutions. So where the gap function was even on the Matsubara axis. There can also exist odd frequency solutions like this, where there's only one node here, for instance. But these odd frequency solutions typically require coupling strength, which is of order 1. And then you can basically study, so these odd frequency solutions, on the one hand, they kind of don't really depend on this repulsion. The kind of repulsion drops out from their gap equation. But on the other hand, they're easily killed by the self-energy effects if you include self-energy, because self-energy normalizes the coupling like this, and then basically you cannot get lambda equal order 1 so easily. But if you find a regime where this odd frequency solution actually exists, and it even coexists with the even frequency solution, then you can get a spontaneous breaking of time reversal with the order parameter like this. So that's truly the end, and thank you for the attention. Let me say that this is published and will also be published in the journal soon. And you can also find a nice summary by Jörg Schmalian of this on the Condensed Matter Journal Club website. Thank you.
Thank you very much. In my subjective opinion, these results are beautiful.
Thank you.
Questions from Fabio Ribeiro.
Yes.
Are you hearing me?
Yeah.
So thank you, David, for your space. Dimitri, nice talk. Amazing results. Look, in some moments you mentioned about topological transitions. I would like to know if you have investigated about the universality class. What is the universality class?
I mean, okay, so I'm not sure whether this is. You really mean the say the critical exponents or so of this transition?
Yep.
So we haven't really done this. I mean, so I cannot really say. I mean, it's some kind of a continuous transition, and in principle, yeah, maybe one can do something. So, but now we just have this kind of mean field picture. We didn't really study any AG description of this. So I haven't studied this yet. Yeah.
Right. Thank you for your answer.
Yeah, thank you.
Okay, thank you very much.